Section 6.8 Average Power in the Wind. Section 6.8.1 Average Power in the Wind. The cubic relationship between power in the wind and wind velocity tells us that we cannot determine the average power in the wind by simply substituting average wind speed into equation 6.4. We can begin to explore this important nonlinear characteristic of wind by rewriting 6.4 in terms of average values. The average power P average is equal to 1.5 rho A V cubic, the average value of the 1.5 rho A V cubic, which is since rho is air density and A is area, those are constants. Therefore, the average power is equal to 1.5 rho A multiply V, the average of the V cube. In other words, we need to find the average value of the cube of velocity. To do so will require that we introduce some statistics. Discrete wind histogram. What do we mean by the average of some quantity? Suppose, for example, we collect some wind data at a site and then want to know how to figure out the average wind speed during the measurement time. The average wind speed can be thought of as the total meters, kilometers, or miles of wind that have blown past the site, divided by the total time that it took to do so. Suppose that during a 10-hour period, there are 3 hours of no wind, 3 hours of 5 miles per hour, and 4 hours at 10 miles per hour. The average wind speed would be average wind speed V average is equal to the total miles of wind divided by the total hours. Since a 3 hour has no wind, so 3 multiplied 0 plus 3 hours have 5 miles per hour, 3 multiplied 5 plus 4 hours at 10 miles per hour, 4 multiplied 10. They are divided by the total number of hours, which is 3 plus 3 plus 4. So the total miles is 55 and the total hours is 10. So the average wind speed is 5.5 miles per hour. We could write 630 in more general way. The V average is equal to the VI multiply the number of hours at VI and then sum all the VI, all the number of I together divided by the number of total number of hours. So the V average is equal to VI multiply the fraction of hours at VI. If those winds were typical, we could say that the probability that there is no wind is 0.3. The probability that it is blowing 5 miles per hour is 0.3. And the probability that it is 10 miles per hour is 0.4. So then the average value in the probability should be the average value of V average of wind speed is equal to the sum of VI multiply the probability when V equal to VI. We know from 6.29 that the quantity of interest in determining average power in the wind is not the average value of V, but the average value of V cubic. The averaging process is exactly the same as our simple example. So the average value of V cubic is equal to the sum of Vi cubic multiplied the hours at Vi divided by the total hours, which is equal to Vi cubic multiplied fraction of hours at Vi. In terms of probability, the average of V cubic is equal to Vi cubic multiplied probability when V equal to Vi. Figure 6.23 shows an example of site data and the resulting wind histogram showing hours of that wind blows at each wind speed. The x is wind speed and y is the hours per year. So as we can see, when the wind blows at 0, the number of hours in total year 8,760 hours is 24. So among 8,760 hours in a year, there is 24 hours no wind. And there is 896 hours among 8,760 hours in a year that wind blows at 7 meters per second. So among 8,760 hours in a year, there is 164 hours the wind blows at 15 meters per second. Section 6.82, wind power probability density functions. The type of information displayed in the discrete wind speed histogram in figure 6.22 is very often presented as a continuous function called probability density function. The defining features of a probability density function is shown in figure 6.23. The area under the curve is equal to unity. So the total area under this curve is equal to 1. The area under the curve between any two wind speeds equals to the probability that the wind is between those two speeds. For example, this area, the area between the V1 and the V2 shows the probability is equal to the probability that the wind is between V1 and V2. Expressed mathematically, if we assume Fv is the wind speed probability density function, the probability V is between V1 and V2 is equal to the integral of V1 to V2 Fv multiplied dV. The probability between V from 0 to infinite is the integral of 0 to infinite Fv multiplied dV. That should be equal to 1. That represents the total area of the probability density function curve. If we want to know the number of hours per year that the wind blows between any two wind speeds, simply multiply 8,760 hours per year. So the hours when the V between V1 multiplied V2 is equal to 8,760 multiplied the integral of V1 to V2 Fv dV. The average wind speed can be found using probability density in the same manner as it was found in the discrete approach. So the V average should be equal to, from 0 to infinite, V multiply Fv multiplied dV. The average value of the cube of velocity also analog to the discrete version. So the average of V cube is equal to the integral from 0 to infinite, the v cubed multiply fv multiply dv. A very general expression that is often used as a starting point for characterizing the statistic of wind speed is called the Weibull probability density function. The Weibull probability density function is equal to Fv is equal to k divided by c multiply v divided by c, the exponential k minus 1 multiply the exp, the bracket minus v divided by c k, where k is called the shape parameter and c is called the scale parameter. For k is equal to 1, it is like an exponential decay function. It will probably not be a good site for wind turbine since most of wind are at such low speed. For k is equal to 2, the wind blows fairly consistently, but there are periods during which the wind blows much harder than the motor typical speed bunch near the peak of the PDF. For k is equal to 3, the function resembles that the familiar bell-shaped curve, and the side would be 1, where the wind are almost always blowing and doing so at a fairly constant speed. When the shape parameter k is equal to 2, the PDF is given its own name, that is a Rayleigh probability density function. So Fv is equal to 2v divided by c squared exponential p minus v divided by c squared. The impact of changing the shape parameter c for Rayleigh PDF is shown in figure 6.25. Larger scale factors shift the curve toward the higher wind speed. There is a direct relationship between scaling factor c and average wind speed v. Substituting the Rayleigh PDF into equation 6.39, and then we can get the v average v is equal to from integral 0 to infinite v multiply fv multiply dv. Substitute fv using the Rayleigh PDF, we can obtain the integral of 0 to infinite is equal to c squared 2v squared exponential e minus vc v divided by c squared, and is equal to 0.0086 c. In other words, c can be expressed as 1.128 v average. This is a figure 6.25, the Rayleigh probability density function with a varying scale factor c. As we can see, it is c4, c6, and c8. As the c increase, higher scaling parameter corresponding to high average wind speed. When c is equal to 4, the average wind speed is equal to 3.5 meter per second, which is about 7.9 mile per hour. When c is equal to 6, the average wind speed is 5.3 meter per second, which is about 11.8 mile per hour. Where c is equal to 8, the average wind speed is 7.1 meter per second and 15.9 mile per hour. Section 6.8.3, Weibull and Rayleigh statistics. Even though equation 6.44 was derived for Rayleigh statistics, is quite accurate for a range of shape factors k from about 1.5 to 4. Substituting equation 6.44 into 6.42, we can find the Rayleigh PDF in terms of average wind speed. The Rayleigh PDF is equal to pi multiply v divided by 2, the average v square multiply e exponential minus 4 pi v divided by v average v square. Section 6.8.4, average power in the wind with Rayleigh statistics. Substituting the Rayleigh PDF using the equation 6.42 into equation 6.40, we can find that the average value of the cube of wind speed, which is equal to the 3/4 c cubic divided by the square root of pi. So the average of v cube, which is about 1.91 v average v the cube. Equation 6.47 is very interesting and very useful. It says that if we assume that Rayleigh statistics, then the average of cube wind speed, the average of cube wind speed is equal to 1.91 times the average wind speed cubed. So if we assume Rayleigh statistics, we can rewrite the fundamental relationship for average power in the wind. The P average power in the wind is equal to 6 divided by pi multiply 1/2 rho A v the average wind speed cube. So with Rayleigh statistics, the average power in the wind is equal to the power found at average wind speed multiplied by 6 divided by pi, or 1.91. Figure 6.26 shows the probability density function for wind at Altamont Pass in California. A Rayleigh PDF with the same average wind speed of 6.4 meters per second. Section 6.8.5, wind power classification and US potential. The standard power table 6.5 shows the standard wind power classifications. Assuming include Rayleigh statistics, ground fraction coefficient alpha is equal to 1 divided by 7, sea level 0 degree, and air density 1.225 kilogram per meter cubic. And also the 10-meter anemometer height and the 50-meter hub height. So the wind power class 1, the average wind speed at 10 meter is between 0.0 to 4.4 meter per second. Is about 0 to 9.8 mile per hour. The wind power density at 10 meter is about 0 to 100 volt per square meter. And at 50 meter, wind power density is about 1 to 200 volt per meter square. For the Wind class number 2, the average wind speed is 4.4 to 5.1. The average wind speed at 10 meter is 9.8 to 11.4 mile per hour, and the wind power density at 10 meter is 100 to 150 volt per square meter. At 50 meter is 200 to 300 volt per square meter. Up to there are 7 wind power class. The 7 is average wind speed is 7.0 to 9.5. Average wind speed at is 15.7 to 21.5 meter per hour. The wind power density is 400 to 1000 volt per square meter, and wind power density at 50 is 800 to 2000 volt per square meter. This map shows the United States, the regions of equal wind power density based on the above assumption. There's a broad band of states stretching from Texas to North Carolina, North Dakota, especially with high wind potential, including large area in class 4, the better wind over 400 volt per square meter. Now we complete the section 6.8.